Hey, what's up? It's your boy, Jim, and today we're going to talk about something that's pretty dang spectacular, pretty amazing, pretty, well, probably not consequential to your life or anything like that, but to me it's pretty special because, well, I had to learn it for a grade, so there's that, but no, it's pretty special because what we're talking about today, Horspool's algorithm, is a incredibly efficient way to search for strings, substrings in a stretch of long strings, or search for certain characters and what have you. Now, to just call it Horspool's algorithm is a little bit of a disservice to the work that was done before Horspool came along. The official name of this algorithm is the Boyer-Moore-Horspool algorithm, and that's because by the time that Nigel Horspool had published this algorithm in 1980, it was a extension on the work that Boyer and Moore had already done on their string searching algorithm. It's just a slight modification that helps the string be more dynamic in its program. And that's what Nigel Horspool liked to focus on when he was a professor at the University of Victoria, in 1980. Now, in order to demonstrate to you how this algorithm works, I'm going to be using my whiteboard here a little bit, so you're going to see a lot of my backside. I'm sorry you have to witness that, but it's necessary for you to know the full effect of what this puppy can do. Now, let's say we have a string. Let's come up with a string real quick. So our selected string here our selected sentence is, my friend is Joe. He is cool. It's a basic sentence. It's not the longest thing in the world. We're not trying to search through any sort of, Roman epics. We don't have the Iliad here. But what we are trying to do is demonstrate how this thing works. So the first part of this algorithm, the thing that really sets it up is we create something that's called a match table, a bad match table. So to construct this bad match table, we have to know what we're looking for. In this case, I'm going to look for the word Joe. So what we're looking for is J-O-E. And what we have to do with that is we have to put it in a table. Hence the name bad match table. So in this table, we're going to have 4 entries. Because the string itself is a length of 3. And then we also have to have an entry for all other characters. So we have J, O, and E. And in order to find the key values for every other aspect of this string, we have to use a certain formula. Now, this formula just so happens to be the value that we're looking for equals the length of the string minus the position of the character minus 1. So, how does that translate into this? I'm glad you asked. So we have, what we need over here is our value. And in order to obtain that, we take the length of our string, which is 3. We take the letter that we're looking for, the position in the string, so we would have 0, 1, 2. Because strings start at 0 normally, unless you're weird. So we take 0, and then we subtract 1 from it. Because, our string index is only 0, 1, and 2, but we have to start from the string length of 3. So we subtract 1, and we're left with 2. So this equals 2, obviously, so we put 2 there. We do the same all the way down. Minus 1, minus 1, equals 1. And then the last one, the last character is a special exception, because the last character is always just going to be the length of the string, this here. Now, this little asterisk that I've written on the board here is kind of a special character. Not in the sense that it's any one character, but it is every other character that does not hit one of the entries in this table. So, and just the way the algorithm works is we're just going to put the length of the string there too. Now the reason why it works like this is if we come across, let's just throw it right in. So we'll go ahead and we'll put Joe, J-O-E, right there. Now, these two don't matter. They don't matter all that much. What does matter is this bad boy right here. Now, what comes down through this section right here is a space. So you might not consider space a character, especially not in normal English, because, you know, space is usually the absence of a character even. But with computers, every single bit counts. And what space falls under here is our little asterisk. So we see that's a 3, and we go ahead and we advance 3 spaces. We go 1, 2, 3. We put Joe down here. And we look at what's right here. Same thing. R in friend doesn't hit any of these characters, so it again falls in the asterisk. So we keep on going. We say J-O-E. Now we actually have a match here. So what this algorithm thinks is, oh boy, we might have found part of the mystery string that we're searching for. Now let's take a minute to talk about what's actually going on here. You and me, as humans, as actual people, well, I hope you're an actual people, if not, we can just look at this and say, there's Joe. But computers can't do that. They don't have eyes, at least not when looking at strings, and especially not when manipulating data on their processor. So what they have to do is they have to go by and make a comparison each way down. Now, comparisons are ridiculously expensive in a processing unit. It's one of the most expensive operations that you can do in most cases, unless you have a specialized processor. So what makes this algorithm work in its special way is that it's eliminating a lot of the comparisons that you have to do. Instead of going down the list each and every time and saying, all right, it doesn't match J, it doesn't match O, it doesn't match E. It's actually going down and it's skipping the things that we don't want. Now in this case it's not that extreme because the substring that we're looking for is only, 3 total characters. But if you were searching through an essay for, some long convoluted technical term or something like that, anytime there's a miss on one of these characters, it's going to skip that entire, or at least a portion of that convoluted string. So, in this case, we hit an E. So, we're advancing 3 spaces anyway, but the point still stands. We go J-O-E. So we hit another space. Now I'm actually going to start erasing here to make it less confusing. So we say J-O-E, hit an S. We say J-O-E, hit a. Now we've actually entered the string that we're looking for, this little substring here. This is what we're looking for. But the computer doesn't know that. It just sees that, there's a boo-boo there. So that's one of the reasons why the E will always, or the last letter of the substring, will always be the actual length of the string. That way, if you get a situation where you just barely miss it, you snag the very edge of it, you're still going to be able to move over and actually find the string. Because when we do what we usually do and move over, J, O, E, we have a match. So we hit a match here, right? That's good. We hit a match here. That's good. We hit a match all the way down. You found your substring. And that's the gist of this algorithm. It's relatively simple when you break it down. It can be a little daunting at first if you've never worked with things like bad match tables or something like that. But in short, there's a lot of benefits that using something like this offers. Now, let's talk about performance and complexity a little bit. Now, in general, this algorithm, just in the way it works, it's not too intensive on space efficiency. It is a little bit less efficient than something like a brute force algorithm because you are having to make that table for the computer to reference back to. When you consider that you're only trading, a couple bytes of space, if that, to make a table for the computer to look back at, versus having to search every single little bit of that string for your substring, you start to realize that with the Horspool's algorithm only having an average time complexity of big O of n, where n is the length of your string, it turns out pretty okay. Even in its worst case efficiency, where it's big O m of n, where m is the size of your substring and n is the size of your total string, you realize that it has a much more efficient inner loop structure as well as a much more efficient space saving structure than just the Boyer-Moore algorithm, which we really didn't talk about much this video, but everything that the Boyer-Moore does is encapsulated in the Boyer-Moore Horspool's, which is Horspool's algorithm, in a better fashion. And in the case where you're searching for a particularly long substring, that's actually where this algorithm shines, because the longer the substring gets, the faster this algorithm picks up. And the reason for that is if you have a longer substring, that match table that I just erased for some reason is going to be even bigger, and if you hit the very edge of that string and nothing matches, it's going to skip, your entire ribonucleic acid substring or something like that. Anyway, that's been my explanation, Jim's explanation of the Horspool's algorithm. We're going to see how far we get with the current production equipment that we have, being my phone propped up on the back of my office chair and a free trial version of Adobe Premiere. But hopefully I'll be able to strap together something that actually makes sense and works for you. Thank you, and that's all.